you should they ask yourself why are we using mean squared error for it instead of just using a normal one. So when you take this example here, so when you take this example here, see there's a network. You can see here they have one network output. There's a network output here and there's a target output. Network output and target
Yes.
output. And this arrow here is using target minus actual here. So they take this one and subtract the 0.4 from it. They take this and subtract this one from it. They take this and subtract this from this. That's what like initially that's the this is the error that we are not that's what we have been using so far. So that's what they had. And now you're using an absolute error. They're using the same thing, but this one you're just taking the absolute value of it. Meaning you will not see anything like negative here. The negative is not turning to positive like this one. The absolute value for this value for this figure here is 0.1. See. So this is what you also have in here. And there's the squared error. Target minus the actual all squared. So one thing you're supposed to know that when you use this error, the normal one, the target minus the actual, you can see the summation of all these values will give us 0. The summation for all these values will give us 0. That's why you can't use this error function. You can't use this error function because you can see the network is not really predicting the thing very well. But this error function is just trying to tell us that our some error is 0, meaning our network is doing very well. When you check it very well, I can see this is our target output, and the network output is this. See, the network output is not being able to predict the target output correctly. So, I mean, this error function is not it's not good. If you want to calculate the performance of our neural network, it's not good. We just have to get a new one. But when you also watch this absolute value, when you see this absolute value, you can see this absolute value, even though it's doing well as compared, is doing better than this one. When you should draw the graph for this absolute value of this error function, this error function will have a very sharp edge. Yeah, if you draw it, it will have a very sharp edge where you see something like a V shape, and it's very difficult for us to find the slope or the minimum point on the graph. If you're supposed to use a gradient descent to calculate for it. See? But the last one of what we used
Yes,
the
sir.
last one of what we used that was the target minus output all squared. So this is going to give us to give us like a slope, a curved graph, a graph that looks like a C that they've turned it like 90 degrees onto clockwise. And see. So the last one is what we can really work with because it's very difficult.
Okay,
It
sir.
will be easier for us to find the minimum points on that graph. So that's why you're not using this one, you're also not using this one. And many people also use a different error function depending on the data they're working with. But for simplicity's sake, you're just going for this one, the squared error. Hmm. So how do you update the weight? How do you update the weight of error propagation? We can use a mathematical formula just calculate for it. We can use a mathematical formula to calculate for this weight. Even mathematical expression can calculate for this weight. But that's not what you're going to use, or that's not what we should use because one thing you also have to know is that one, we are doing a prediction. Meaning we are not having accurate data, or we are not having a perfect data. Because some data can contain errors. Some people will just be recording data, but they will make a mistake somewhere. So we don't have a perfect data to make the predictions. So you can't just get a very straightforward mathematical formula for this. See, that's why it's good to be a bit pessimistic. We have to be a bit pessimistic because if you use a gradient data, it's not trying to use all the data just to make a final prediction. He just tries to update everything bit by bit, just to find a slope bit by bit. And in most cases, even though he can't, even in most cases, he can find a slope, but it's not always that he's able to find the slope. That's why it's good for us to use a gradient descent and just using a mathematical expression for it. And when you check this formula, if you're supposed to use you're supposed to use any of this one, like maybe the target one's actual. It's very easy for us just to find to find the slope for this one. It's very easy for us to find. You see, to find a
Yes, sir.
to find a mathematical expression for it. But we don't want that way. We just want to just be pessimistic here. Just try and go step by step to find for us to or to be able to update our weights. And once we're talking about how to update the weights, some people can some people can we talk about brute force all the time. So we can also use a brute force approach to be able to update our weights, to be able to update the weight. But that's not what we want to use now. You don't want to use a brute force approach. We talk about this the other time. Like we just try to combine, you just do many combinations of the weights and see if we change, maybe we just take three weights. We just take random numbers, one, two, three, and see the output we are going to get for the we just see the value you are going to get for the final output. You see. Maybe the first one use one, two, three.
Yes, sir.
The next one can use something like two, four, five to do it. But that's not a good approach because if you're supposed to keep changing numbers a lot of time, it's going to really take a lot of time perhaps to update it. And from this one, you can see one of them, if you're doing a five by 500 by 500 neural network, 500 by 500 neural network, it's taking almost like 16 years for it to be updated. And that's not a very good way to train a neural network. So this brings us to a gradient descent. We're going to use a gradient descent to update our weights. Gradient descent to update our weights. Right. So that's how it goes. When you watch this graph very well, see, just watch this graph. And with this graph, this how the square error looks like. What he said, the square error. This how the graph looks like. So this square error, the error you are using here, this error graph, it looks like this. It looks like this. Why do you check this error roller? Because we know from our basic education that a slope, anything like any line that comes from this side is negative slope, and any line that comes from this side is positive, which is positive. That's what you know.
Yes, sir.
So you can see that this one, they're just trying to come to this side. They're just coming to come to this side. They're trying to come to this side here. And again, this is a two-way. This one started from here, and it wants to reach this side. So it started from here, and the next step it took was this side. But since the slope here is negative here, it's negative, you can see that the x value, initially the x value will be somewhere here. But if it is to reach here, the x value will be somewhere here. Consider x have increased from this side to this side. And also in the same way, you can see that when it started from this side, here the x value was supposed to be here. And then when we moved to this side. And here x was already here, and they moved backwards. And it's moved backwards. You can see that with the negative side, you increase the x value here. But with the positive slope, your rather was decrease the x value here. You rather decrease the x value here. That's why you're saying that we increase x in the opposite direction. You see, if the slope is negative, the x has to be increased. If the slope is negative, you have to increase x. But if the slope is positive, you have to was decrease x. So a positive gradient means we reduce x. A negative gradient means we increase what x. A negative gradient means we have to increase x.
Yes, sir.
Okay. So this one thing is also have to keep it in mind. Okay.
Okay.
All right. So now let's take a look at this diagram. Let's take a look at it very well. Just take your time and just look. Even don't just look at the symbols and everything you're using. The OK, WJK. here. Take note of the symbols you're seeing. Take note of the symbols you're seeing here. You see, that's what you're going to use to do a gradient insert. You can see that the can see the OK. Okay, what do you think? What does the OK means? The OK that you see, the O with the subscript of K. What does it mean?
Okay, so the OK means the output of the K layer.
All right, output of the K layer. Okay, right. You can it's true. The output of the last layer. That's for OK. It's true. That's for the last. And the TK is a truth of that layer, like the truth data or the one you're trying to predict. You can see the EK is just the error, the error between the true data and the actual output that we had. All right. And you can see that here is having I here, XI is just the input here. And this one is supposed to be J, this one is supposed to be J. And the hidden, this for this side is supposed to be J. That's for the hidden layer. And the output layer is just having a K. The representing the output layer by K. And the input is just I. So if it's to move on, we are using about a squared error, but you need to find that some of the total errors that we are getting from our neural network. If you have a lot of data, we have almost 1,000 data points. You need to just find all the errors that we are having from our neural network. You're just trying to sum everything and compare it towards the other training example that you've done. The one with the lowest summation will be the neural network. Will be the neural network that should be preferred or that we can use because that's the one having the least error. See, so this is the error
Okay,
code we
sir.
are going to. This is the error
Sir,
code we
please,
are
a
going to.
question.
Yeah.
Sir, please, after finding the sum of all the errors, they choose the lowest error. So, sir, I'm
Yeah.
asking, why don't they find the average error instead of choosing the lowest error?
That's good. That's a very good idea because if you should keep doing this thing for a very long time, you can also all implement your own way of the one you think this will help to improve the network. You see, because if you have apply the availability, you try to be a bit unbiased instead of just always going for the list one. You try to be unbiased. That's also a good idea. But yeah, we just want to do based on the basics, just the idea or the simple basic for it. It's also a good idea though. It's fine. But if you should find the
Okay,
average,
sir.
you need to work on a lot of stuff to do it. Because the average, me, if you find the average, I know what weight length are you going to use for the average. I also going to find the average for all the weight lengths. Because if you just take the lowest
Okay.
here, the least error here, it's already having its weight length and everything that came randomly. But if you're finding the average, how are you going to find your weight length and all those stuff? But I can also work out on those kind of stuff too. That's what I'm saying. Depends on you. When you keep on working with this, you also know the best way you can go about it. You can know the best way you can
Okay,
go
sir.
about it.
That would be great.
Yeah. All right. So let's continue. All right. So, but when you just check this diagram, you can see you have something like ON here, ON and TN here, because you're doing a summation over all the data points are supposed to, all the inputs are supposed to train, on it. That's why you're seeing N here, because about the diagram was just showing K here. There's some all the N are supposed to train on. Right, so that's what you're having here. So now, because you're dealing about variance, I mean, you want to find the slope of this one. You want to find the slope or the minimum point for this error. How do you get a minimum point for this error? That's what they're going to do. That's why you are trying to apply Python. Trying to apply calculus to it. Why are they using calculus? Because to find the slope or the minimum based on the weight, because what they're trying to do here is that if we change the weights, how is it going to affect our output? If we should change the weight, how is it going to affect our output? That's like the rate of change of our output with respect to the rate of change of our output with respect to our weight. That's what calculus deals with. It always deals with a rate of change. It is a rate of change. Like if you apply a force to
Okay.
a spring balance, how would the length change? You can use what? Our derivative or our calculus to find for it. So that's why you're using a differentiation here to find for our slope here. So the derivative of our E with respect to our WJK. And you can see here you can see that WJK, when you just follow the diagram, see the WJK, see our this is our K. So the K is just our output layer, and the J is our hidden layer. So meaning you're only dealing with the hidden and the output layer here. Anything other than is just the hidden, and there's a hidden and the output layer you are dealing here. We can apply the same idea with the inputs and the hidden layer. Okay. Right. So that's what they are doing. So here you can see they've changed the E here to this formula here. So the E has been just replaced by this. So you shouldn't confuse yourself. The E here has been replaced by this. This you're seeing here because initially we said our E error is just this function here. All right. But you can see we can remove all the ON from the sum except the one that's the weight the WJK links to. That is okay. You see, we say WJK links to, and that's also true because guess what here? This is our WJK. This is our WJK. And this is our J and this is our K. And our K here is, I see this link here. I see this WJK. They're just linking to this one here. They're just linking to this node here. Meaning we don't care about all the other ways here, like all the blue ways. We don't care about it. The only thing we care about is this one here. But these are the only links that's connecting to this node here. These are the only links that's connecting to this node here. We don't care about any other nodes again. I don't know if you understand what I'm saying.
I understand, sir.
We don't care about any other node. We really care about what is being displayed there. Come in. So you really care about what is being displayed there. All right. So you can see the K here, the K here is equal to 1 and K is equal to 2 here. So meaning this node 1 and this one, even though they're just represented by K, so here will be something like, let's say, here this WJK will become W11 here. Here become W21. Because they are the only people, they are the only links that's connecting to this first node here. The only links that's connecting to this first node here. That's connected to this first node. So that's why you're saying that we can ignore all the ON. All the other out, we can just ignore them because we're not concerned about it. We're really concerned about just one weight. We're really concerned about just one because we just want to update just one weight. Just want to update just this weight here. Just one WJK, just one of these weights here. We don't care about any other weights. That's why I say you can ignore all the other ON and just leave the OK and this one. I mean, if this one changes, how is it going to affect the output of this? So why are we using OK instead of TK? All right. So now you can see this from here. We are still dealing with the derivative, and that's what we have in here. So, but we know that TK is our truth value here that we are trying to predict. Now, and the OK is our actual value that we have from the neural network. So you can see this TK here. The TK doesn't change. No matter what you do to our weight, it won't affect the TK. No matter what you do to our weight, it won't affect the TK. So the only thing that that's going to affect us, if we change our WJK, the only thing that will be affected is the OK. So when you apply the chain rule to it, you should do it in terms of our OK. You can't do it in terms of our TK. You can't do it in terms of, because the TK doesn't change. It's the OK that rather changes. So that's why you can see we apply the chain rule to it. The chain rule of E with respect to our change of OK. time the change of our OK with respect to our change of our WJK. You're not using T because the T doesn't change. The only value that changes is our OK. If WJK is going to affect OK. So now as we continue, you can see that this one is just our change of our error with respect to our OK. Change of our error with respect to our OK. And change of error with respect to our OK. With our OK is this, well, this was we're going to get. Because this is our error function, our E function here. If we should find the derivative with respect to our OK, it's a result of OK. But here it doesn't O in here, but if you are working on it, it's just supposed to be OK. If you should find a derivative with respect to OK, you're going to get something like this. You're going to get something like that. And by this one, they've not applied anything to it. They're just leaving it as we are seeing it here. So find the derivative for this error here. It give us something like this. But as we say, we don't need all the other O, and we're only concerned with the TK and the OK. We're concerned with TK and the OK. So continuing further, we can see that this OK is just this OK here. It's just the output from the last layer. If you watch this very well, is the output from this last layer here. And the output from the last layer, you can see when you apply the segment function to this, to the input into the side, that will give us our output, the input. And how do we find the input? The input is just a summation of all the weight links times the input from this side will give us the input into this side. See, in the way I just apply the segment function to it. So that's what you're seeing here. You can see that we just do the summation for all the WJK times the OJ. You see they're using OJ because it's coming from the previous, the one coming from the previous nodes. The one coming from the previous node. See, the one coming from the previous node. So this one,
Yes, sir.
is just the one inside here. The one inside here is just trying to find the input into the node. The input into the node. So when you just check here, the input into this node here, you have to take the inputs here times the weight link here, the inputs here, and the weight link here. And the weight link here. See, when I'm done, then you apply the segment function to it. So that's exactly what I'm seeing here. You just find all the summation of the weight link and all the weight link and the input on the previous layer. So when everything is done, when you apply the segment function to it, that'll give us the output from that node. That's what you're seeing, because the OK is the output from the node. And if you expanded it into its main form here. And that's what it's showing here. So if we just continue, you can see that the only thing left is for us to, so we now have to find a derivative for this. With respect to the WJK. The reason why we need to expand this is because we can't just find the derivative of this one, especially the WJK, because there's nothing like the WJK inside of OK here. So that's why I expanded the OK here to its form. So we can now find the derivative of this one with respect to the WJK. So if we find the derivative for segment function, this is the derivative of segment function. We're going to get something like the segment of x times 1 minus segment of x. And the only thing you're supposed to just have to play the x by the function that we are seeing here, this value here. Play the x by this. And if you should play x by that, then this is what you're going to get. This is what you're going to get. This is what you're going to get. And if you should move further again, you can see. Okay, you can see that that's what you're going to get. If you know this 2 here is the derivative of our segment. But to find the derivative of our segment, you also have to find the derivative of the function inside the segment 2 again. The function inside the derivative of the function inside or the expression inside the segment function again. So that's how the rules of the calculus also works. So if you find the derivative for this, the only thing we should differentiate with respect to the WJK. So all these ones will cancel, and so all these ones will be cancelled, and just be left with OJ. Just be left with OJ. Left OJ because we don't need any other outputs again. The only output that we need is just this OJ here. So let's, you can see it's left with OJ. Right. So if you got in it, so that's why now they also took us through an example. So the main thing you're supposed to know, no, yeah, you can take up the two because our main focus is about the direction of the slope. It's not about like it's not about this is just a scalar that's just multiplying. Our main focus is just about direction. You see? So you can see here they've taken up the two from this side. And here I think they are this one they are just trying to do the same thing for the input layer and the hiding layer too. So the only thing you have to know this from like the error that if you want to find the derivative or the slope of the error is just this negative times the error times the sigmoid of this function here. 1 minus sigmoid of the expression here. 10 times OJ. And to really update our weight, this is what we're going to do. To really update, you have to take the new weights we use because the old weights, the WJK old weights, they just have to apply minus a learning rate times or the slope we are getting. So if you should just find a slope for it, what we are getting. The reason they are just they apply the negative sign here, they just want to go, as we saw initially, just want to go opposite to the slope of the arrow we had. The slope that we had, just want to go to opposite. So you can see by this error function already have a negative sign, so this will just cancel each other. Just cancel each other. And here just what they're just trying to do here, they're just trying to convert everything. Instead of just doing here we just did it, but we just did the weight update. We just one single weight link. They're just doing the weight link from J to K. That's the only thing we did. But if you want to just do it for all the weights, so they can just work on it very, very fast. So that's what they are trying to do. So if you just multiply, consider this one, we just multiply the error times the segment function, 1 minus the segment function, like what we are seeing here. The same thing I'm seeing here, but they're not bringing a negative because I said the negative could just cancel. Times this one, times this one. Then you just have to bring the output as a O1 times O1. Why is it 1? Because it's 1 because you can see that at the end of the day, when the graph, what we had from here, you can see he's going to WIJ. But the last one was just I here. You can see that any value, let's start with this one, will just become the last one as the output. The W11, you can see the last part will have to become O1. Then this one to the same thing, W1 to the last part was O1. But if you come here, W21, the last part will just be O2. If you do the matrix multiplication, you can see the same thing as what you're seeing. But this time you're just doing it for all the weight link. You're doing from all the weight link. So this will be the matrix representation for all the weight link. If you want to update all the weight link together. So just so the change of the weights. So if you should apply it with the change of the weight link will just be called. This is a change of the value I was supposed to add it to our weight. Just because our learning rates, that's the alpha times the error times the output from our last node. And this one they are just converting what we just did. They are converting this thing here. Here the root segment of, but segment of or the summation of the Wij times Oj will just give us OK. If you watch it very well, this one is just trying to do something like this. What he's just trying to do is taking the weight here and multiplying by the input here. Taking the weight and multiplying by the input. If you find the sum of it, it's going to be the input into this one. It's going to be the input into it, this one. And when you apply the segment function to it, just going to your output, that's OK. That's what we are doing here. That's what they're doing here. That's what if we change everything to EK, they change everything to OK because OK will just be the output from it. 1 minus OK times the OJ transposed. Times the OJ transposed.
Okay, sir.
So you are seeing the transpose because they're now writing everything in the matrix notation form. See this one. There's a transpose. The OJ has been transposed. That's what you're seeing in this way. All the outputs. So if we should just take an example. If you want to update this one, W11, because if you want to update this one, W11, because even here they are saying W12, well, let's just try and take something like this, W11 equals to 2.0. How are you going to do this update? You should update this one now. From the formula you're having, how are you going to do it?
Okay, sir. Okay, sir. So to update the W11, we need the output for layer 1. That's the OJ, and we need the error for um the we need the error for the output layer, which is E1.
Right. So let's try and
Yeah.
do it one by one. Let's try and use this formula for it. Okay. Let's try and use this formula to update it. So we know that let's find our EJ. Let's find our EK. This one is the input and output. Let's try and find our EK. But EK error, no, you can see that with this one. This one is W11, so meaning it's going to the first node here. It's going to our first node here. And the first node, the output they had was what? The error they had was 0.8. So we've already gotten an error. This error here, we've gotten it. So the error here is 0.8. Do you agree? Sure. Do you agree?
Yes, sir.
All right, because this first thing, if you just what they're going to say, the first thing you're supposed to find is just our error here. That's what they say. There is our error. Let me just use the other one. If you use the one, let's say the first thing you're supposed to find is our error. So find the error. When you're then done, we just have to find the output. How to find the output here. You see. So now from this diagram, you can see the error here. We didn't calculate for it. They've already written it for it. They've written it there for us. So it's 0 and 0.8. Then when you're done, you have to find the output from the what? From the side. Let's find the output from the side. Because from the what if you watch the diagram very well? The next one is the next you're supposed to do. You just find the what? After we get the error, the error is already have a negative, we know. So we have to find the error just to what? Find the output from that same what? The output of that node. The out because the sigmoid times the what? The summation of the weight times the previous from the times the weight times the input from the previous layer. So I mean that's just the outputs of the node that this weight is going to. We know the weight, this weight here, this weight length is going to this node here. So what are we in the left is just find the output of this node here. And the output, all the output of this node. The only thing what you can do to find the output of this node is just multiply 2 by what? OJ is 1. The input from this OJ is what? 1 here. This one, the output from this one is 1. So you have like 2 by 1 plus this node here. The length coming to is this one and this one. Is become 3 plus 2. 3 plus 2. 3 plus 2 because this output is giving out, this node is giving an output of 2. When it comes to this, the node was giving an output of 1 here. That's why I said 1 times 2. Then plus 3 times 2 here. And 3 times 2 here. So what we get, I'll just find a summation of it and just find a sigmoid function of that summation we had. And that will give us the output. And that output will now become the value here. That output just become the value here. You see, you can see this side and this side is the same thing. So the only thing I'm supposed to just have to do 1 minus the value we had for this one, the output we had for this one. 1 minus the output we had for the whole thing here. Then when you're done, you have to just find the OJ. The OJ is the output from that previous sort, the output from the previous layer. The weight was connecting, the weight W11 was connecting to this node here. That's our previous node from the previous layer here. This one is connecting to this one previous layer. So the only thing is supposed to do, our OJ will just become the value here. That's what 1. That's 1. You see. But here they just find it. Yeah, this one they just find it for if you do everything if you should do it, you just have to multiply everything together. When you're done, you just have to use the learning rate, apply the learning rate to it 0.1 because the negative sign just changed. But here they use 1 point, they use W12. Here they use W12 for it. They use W12 for it, and that will also be a different case. You can see the W12 how they work. This is how they also worked for it. So now they were finding for the output. Okay, I don't know if it's the same thing. So W12 is the weight 1 2. So weight 1 2 is this side. So weight 1 2 is this side. So the error here, the first error is 0.5. So if they were calculating for it, I think this one they just went straight for it. They just went straight to calculate for it. I should do it step by step. If you do it step by step, or the formula they are using was a bit, it was different from the one you're supposed to do. But this idea of how you're supposed to work, calculate for the, if you want to update it, there's the whole idea. So if you are, I just want you guys to understand this part so that when you are just writing, or you can even write the code for me to update the weight. See, there's the idea. And even if you should update the W12. The only thing I'm supposed to do W12, you can it sees the weight here. This weight W12. There's the link here. The link is this one here. The number here. So the first thing I'm supposed to do is find for the error, and the error is 0.5 here. And the next thing here is just find the what? Just find the output for this node. Just find the output for this node here. So the output will just become 1 times 1 here plus 2 times 4 plus 2 times 4. Okay, 2 times 4. Okay, yes, this one is a bit different. 1 times. So here become 4. Here become 4 times 2 here. So using 4 times 2 here, 4 times 2 here. And next one become 1 times 1. It's 1 times 1. So that will be for this part. That will be for just this part here. That's this part here. So the value we get for the whole thing, you just take 1 minus that value here. 10 times the what? The output from the previous node. Since we are updating what W12, the only thing I'm supposed to do is the output from the previous node is just this one. But the weight is just connected. The weight that's trying to update is this one. And it's from this side to this side. So the output from the previous layer is just this one here. So the value you had is just 1 here. You're supposed to multiply by 1. What you had is supposed to get, then you are supposed to multiply by the learning rate again to get the change of our W weight. To get a change of our weight. Get a change of our weight.
Hello, sir.
Yeah.
Sir, please, OJ. The OJ, they said the OJ equals 1, and that's what we are using, but they are also equating it to 0.4. I don't know if it's a mistake or
This one that you're using here is not the right one, because there's nothing like 3 here. There's nothing like 3 here. That's why is the 3 you're using? You're updating 1 2. If you're supposed to update 1 2, I think they rather use 1 2 1 here. Let me just start this and just show
okay.
something here.
Yeah. So please, OJ.
I'm coming.
Yes, sir.
So can you see my screen very well? Can you see my screen?
Yes, sir. Yes, sir.
So like this one, if you're supposed to update this one, if you're supposed to update this, you're supposed to update this one. So imagine I want to update W12. I want to update W12. And okay, let's start with W11 first. The W11. Let's start with W11 first. The only
Okay,
thing
sir.
you're supposed to find, what you're supposed to find first is our error. And our error is 0.8. 0.8. You have to do a dot product for it times. And the diagram shows that if you have to find error, the only thing the next one is just find the output from of that node that's connected. The node the weight is connecting to. The weight here is connecting to this node here. That's the output for the what of the output from of this node. The node that is connecting to. So the output
Yes,
from this
sir.
node, if you want to find for the output for this node, the only thing you're supposed to do is take the weight here and multiply by the output from this node here, the previous node. And it's 1 here, so 1 times 2. So here will become
Yes,
1
sir.
times
Sir,
2.
please. Sir, please. The say you see the OJ was 1, but next to
Yeah,
the
so
OJ we have 0.4.
Okay. Sorry.
Yeah, so I was
I
asking
have
which one are we using?
All right. So OJ is so it's supposed to be 0.4. Like this J is just a symbol. I think it's a symbol because this one's representing one. I they know this one. That's why they wrote one here. So it's supposed to be
Yes,
zero
sir.
point
Sir, please,
four.
that was my question.
All right. So it's supposed to be 0. It's not supposed to be one. It's supposed to be 0.4. 0.4 times 0.4 times 0.4 times the two. The weight link here. Then, but this one is supposed to be a summation. Mm.
Yes, sir.
Plus another one. This one. The node here is the other link connecting to this node is this one. It's 3.0 times 0.5. So 3.0 is 0.5. All right, I think that's what you're also trying to have there. So so now we've gotten the output for this one. You see.
Sir,
So
please,
if
then the sigmoid of that is, sir, won't it be the sigmoid of the sum?
yeah, it's really a segment, it's true. So
Yes, sir.
just try and find a summation. What 0.4 times 2 is what? What's 0.4
Sir,
times 2?
0.8. Sir, 0.8.
0.8. So
8, yeah.
0.8. And 3.0 times 0.5 is what?
Sir, 1.5.
So we're going to get 1.5 here. So 1.5 plus 0.8 to give us 2.3.
Sir, yes, sir.
So 2.3. We're going to get 2.3. So apply the segment function to 2.3. What are you going to get? Do you know the segment function?
Sir, please, you are going to get 0.9089.
0.9089.
Yes, sir.
89. All right. So that's what we get getting. And you can see that with this one too, you also have to just find it just the next one 1 minus this value I have in 0.9089, something like this. In
Yes, sir.
times the last times this is the weight you're dealing with. The limit is W11. This is the weight you're dealing with, W11. So you can see, these are the node they're going to, but the node we're coming from is this one. So our OJ will just be equal to this node here. The value for this node was 0.4. That was just multiply here by 0.4.
Yes, sir.
So if we should sort all this one together, the value you're going to get, then you just have to multiply by the just I don't know if you're able to you can solve all this thing from just 0.8 times 0.9089 times 1 minus input this and just give me the final answer.
Sir, please, I had 0.0265.
0.026.
0.05.
So this was a good this was a good here. But I can see that this function here, this slope here, was already having a negative sign. So I just bring a negative sign in front of it. Then
Yes, sir.
so this is just our change of the weight. This is our change of the weight. But with the update, the update too was like a negative times or a learning rate.
Uh,
The update was
the learning rate times our value plus
the update
our old.
very good. The update was something like the old value. The old value was the old value was 2.0. This is our new value. This new
Yes,
value
sir.
here is equal to our old value. The old value was 2.0 minus the learning rate. The learning rate here was 0.1. See?
Yes, sir.
Then times And the slope we had was zero negative 0.0265. 0265. But the negative will cancel. This is having a negative and this also having a negative. It's going to cancel. Here we left with just plus. 80 negative will
Yes,
cancel.
sir.
Yeah. As the negative and negative will cancel, and you have to left plus. So if we should find this the value for this expression here, that will be the value for our new weight. The W11 now becomes will be equal to the value we're going to get.
Yeah. So I had 2.0027.
2.0027.
27.
Yeah, and it's true. It can be true because the learning rate you're using here is a very low learning rate. It's learning at a very low pace, 0.1. So that as I can see, this value is not this value you had here is no different. It's no different from the old one. The old one was just 2.0, but the value you had was 2.0027. So this is how the
Oh,
process
okay, sir.
goes. This is the process you go through to get a new weight. This is the process you go through to get a new
Oh,
weight.
okay, sir. So can it be that this new weight we've gotten, can it be that we can get a better one, although we had a minimum lost?
The main
We used the
so if you get
minimum.
this weight, if you get this weight, if you keep on doing it, this weight will just get closer to a good one, and that good one will
Okay,
just help
sir.
us to like give us, will help to give us a very minimum sum of squared error. It's help us to get a minimum sum of squared error.
Okay, sir.
But it all depends on number of time, it depends on number of time you training. But no matter what, it will always get close to a value. If you keep on doing it, you get close to a value.
Okay, sir.
Yeah, just take your time and just observe it all.
Okay, sir.
So the way to always try to get to close to value, like in mathematics, that's what they used to refer to as is asymptotic. Like asymptotic function, like a function when you keep on adding more value, keep on updating, it always gets close to a value. That's why I say them they always say when n approaches infinity, when n approaches infinity, it's asymptotic. Meaning when n keep on going further, it's always going to get a value. But that's very close to some number.
Okay, sir.
All right, so let me just try and project and see if we can also do. I don't know if what they're doing is also true because me, I was doing something different. Let's try and base the W12.
So the W12.
Okay.
Okay.
So let's try and update the W12. Like W12. You see, here they are saying W12 at this side.
Yes, sir. Sir, I think they made a mistake there.
Yeah, yeah, it's supposed to be a mistake because
Yes,
W12,
sir. Sir,
Because the output from W1 to here, the output here is supposed to be the output is just supposed to be 4 times 1 here, 4 times 0.4 times 1 plus 2 times 4. 2 times 4 is here. Then 0. What? The next one has to be 0.4 times 1. They rather wrote 3 times 0.5. Okay. Let me make a mistake. I think it's supposed to this. Yeah, the output
So
for this
please,
one. Yeah,
the
your first one
connection
4
went
times
out.
4 times 0.5. But here the roots is 3 times 0.5. It's supposed to be 4 times 0.5. See? Because the one connecting to this one is supposed to be 4 times 0.5. But here is 3 times 0.5.
Yes, sir. So even
Then plus.
yes, so I was saying even the W12 is connected to the 0.5 loss, the 0.5 loss, but say they are using the 0.8. That's the root
0.8.
0.8 times. So that's the
Yeah. It's supposed to be
beginning.
0.5.
It's supposed to be
Okay, I think
0.5.
okay, like let's do it for W2 and let's see something. W21.
Okay, sir.
Let's try W2 and see something.
Okay, sir. So we are doing it together.
Okay, you just do it and give the answer. If it's the same thing as what is there.
Okay, sir. So, please, the input into the first layer says 0.4.
Let me check. The input into the
Oh, okay, sir. Is 0.5. Hello, sir.
yeah,
Sir, please, I had 3.0044. 3.
3.0044. Now see they're having a
443.
different one here. Right, so
Yes,
let's try
sir.
and follow it and see. You're updating which one? 2 1 here. So
W21. Yes, sir.
our error is 0.8.
Yes,
Our
sir.
error is 0. Okay, so there's 0.8. And so you become 3 times 5. 3 times 5 then times 2 times 4. Okay, 2 times 4 2 times 0.4, then
Yes, sir.
20. 3 times 0.5. Here is correct. So did you get something like 0.909 for the output?
Sir, no, the output will be 0.23.
Are you sure? After applying the segment function
Yes,
to
sir.
it. 0.23. Why is
I,
0.23?
sir, I think I didn't apply. I said, yeah, I made a mistake. I didn't apply the sigmoid to it.
Yeah, you need to apply the segment.
So you get 0.5572. So if you apply the sigmoid,
All right. 0.5572.
yes, sir.
So if it's 0.5572, then mean here is supposed to be 0.5572. Then 1 minus
Yeah,
0.5572.
yes, sir.
Then times 0.4. But what value did you get for the what did you get for the
Uh,
one inside? What did you get for the one inside?
okay, sir. I made a mistake. Sir, what is inside is 0.95.
0.
Yes, sir. What's inside the sigmoid is 0.9595.
And if you apply the segment, what are you going to get?
So you're going to get 0.7211.
I think they also had it's supposed to be 2.3. It was 2.3. Like what's that previously? What's inside is supposed to
So,
give us 2.
so I had, so I think that one is a mistake because when I tried it right now, I
But
had
you know, 2 times
0.95,
like 2 times 0.4 gives us 8, 0.8 also.
0.8,
Then 3
ah,
times 0.5, 3 times 0.5 gives
1.5.
us 1.5. So
Yes, sir.
1.5 times 0.8 will give us 2.3.
Yes, sir. Ah, sir, I don't know why I'm making so many mistakes, sir.
I think
Oh,
you need
my
to get something like
calculator is in
0.
a different mode.
You need
So
to get
yes,
something
you
like,
get 2.3.
yeah. So we apply the segment will give us what are you going to get? If you apply the segment to
So you get 0.9089.
okay, so exactly that's what you're saying here. So
So yes, you
0.90,
are correct.
1 minus 0.90, and you know we are working with is W21, is W21, and the output for the
Yes,
W21
sir.
is what? Is
So
0.5.
0.5. Yes, sir.
I don't know why they wrote 0.4 here. It's what 0.5.
Yes, yeah. So I think it's a mistake.
Yeah, it's supposed to be 0.4. So if you add a 0.4 to it, the value, you have to know the value supposed to fit.
Yes, sir.
So then the only thing left is for you to just take the old, just have to take the old way. The old way to the limit was 3.0. It was 3.0. Then apply the segment to it. They have to apply the if you are it's 0.3, then minus the alpha is 0.1. So here
Yes,
it
sir.
was minus 0.1.
So I had 0.0330.
0.033.
Yes, 0.0331.
Okay. So if your calculation is correct, I think it's supposed to be everything's supposed to be all right. So I want to show you the idea of how you can go about it. You see.
Yes, sir.
So the task I can give it to you is for you to just what you've seen here, like just write I just give me a Python by when we meet next week or we meet on Sunday. Just give me a Python code on how to
Okay.
just write the update, the how to write the updates for the weight. A Python code that will help us to update the weight.
Okay, sir.
I just if you really understand it, I just try and combine everything together. Just try and give me a weight. a fighting code. But it doesn't necessarily mean that you just go and find, like, go and do a weight. You can just represent the weight by maybe a symbol. You see.
Separately said it. Separately said it
You can
doesn't necessarily.
I said
Hello, sir.
you can
Yeah.
represent it by any symbol, any variable.
Okay,
We just
sir.
want they just want the function that can update the weight for us. The function
Okay,
that can
sir.
update.
Okay, sir.
So, but do you have any question?
Sir, so far